Hello, Year 10. This will be the last lesson of the week. Just to let you know, if you get stuck, please do email me. I am moving house today, so I might be a bit slow with my reply, but I will reply. Now, we're doing about how we hear sound, and there's a few things in this lesson that we haven't covered yet in other parts of the topic. So I'm sure a lot of you understand how the ears work and will be able to Google it and figure it out for yourself. But there's a few things about sound waves we haven't mentioned. Now, first of all, question, and it's kind of like related to something that you learned in last lesson. Why do you not get echoes in a cinema? But say if you were in a sports hall, you do. Now, let's have a look then. We talked about specular reflection versus diffuse scattering last lesson. Same thing happens for sound waves as it does for light waves. When a sound wave meets a hard, flat surface, the sound wave is reflected back because it's kind of smooth surface, right? The sound waves kind of reflect off and you get an echo. Now in a cinema, you'll notice a lot of the walls, and there's lots of carpet, and there's lots of chairs that are soft. When the sound hits the wall, the rough surface, okay, the sound gets scattered in all different directions, and because it scatters into other bits of carpet or wall, it eventually gets absorbed, and that's why it reduces echoes. Okay, now remember, we absolutely should remember that sound waves are longitudinal. Okay, if I follow this vibration here, right, you see the wave is traveling to the right, so I'm going to follow the wave now as it goes past. There's the wave. Yeah, you see I'm following it, right? But if I look at a particle, the particle is vibrating along the same direction the wave travels. So if it vibrates along the same direction the wave travels, it is a longitudinal wave. So first of all, how does sound reach your ear? Well, we know that sound is a longitudinal wave and that you need vibrations, okay? And you need air particles. So when you strike the drum skin vibrates. That pushes the air out the way, essentially. So the vibration of the drum will cause the air to vibrate. Now the compressions and rarefactions of the particles create a sound wave. So when you have, now I'm going to do a quick little drawing here. When you have sound waves drawn like this here, generally the lines represent a compression and the spaces represent a rarefaction. So if I was drawing it as particles, what you'd have on a compression is lots and lots and lots and lots of air particles, right? So here's another compression. Lots and lots of air particles compressed together, because remember, when the drum moves that way and back. So what the drum essentially does is it forces and pushes lots of air particles close together. When it moves back, it's not pushing any air particles there, so it leaves a little space. So you get these compressions here with lots of particles. So this is called a compression. And this bit here in the middle, barely any particles. We call that a rarefaction. So I kept doing this all the way. You'd be able to see the air particles kind of compressed together and spread out. Now, these compressions and rarefactions carry the sound wave to your ear and your eardrum, which causes your eardrum to vibrate. Now, just a quick question. Which medium would sound travel faster through? Is it a solid, a liquid, or a gas? Well, hopefully we've got some ideas of why or which one it is. The answer is a solid, for the reason that if I was to be a sound wave, which remember it's a vibration, and it caused by things bouncing into each other and transferring that vibration along, if I bounced into this particle here, it's already touching the next particle in the line. So the information or the vibration is instantly transferred from one particle to the next. Whereas if I had a liquid, which sound travels pretty quickly through a liquid, just not as fast as a solid. If my sound particle comes in and creates a vibration here, although not much space, it has to travel a little bit before the vibration is transferred. Then this one has to travel a bit, and then this one has to travel a bit. Whereas a gas, if I transferred a vibration here, this gas particle has to travel to here to transfer the vibration, which then has to travel down. Having contact is always going to be traveling. So because all of these are touching, as soon as you hit the desk, the vibration gets pushed through all the particles very quickly. So that is why sound waves travel faster through a solid compared to the other two. Some more facts that we need to know. The hearing range for humans, 20 to 20,000 hertz. Okay? So we have to remember that. The hearing range for humans, 20 to 20,000 hertz. So that 20 to 20,000. And then any sound frequency above 20,000 hertz is called ultrasound. So it's like if you remember this fact, you can remember both. Humans can hear from 20 to 20,000. So anything above that must be ultrasound. So now, hopefully we know this stuff. This is just basically a big recap of everything. So pause it if you'd like to read. And then we're not going to do the exam question. I'd like you to quickly tell me everything that you know about how we hear sound. Okay? Talk about refractions, compressions, talk about pitch and frequency, talk about the structure of the ear, if you can remember that from Key Stage 3. So pause it, spend 5 minutes, 10 minutes, however long you need, writing everything about that. This is task 1. Once you've done that, we're going to go on to actually frequency and pitch, because it is a recap from Key Stage 3. So hopefully you've paused it, you've had a go, and now we're continuing on. Well, if you want to, you can click these buttons here. I'm not going to click them in the YouTube video because it'll make it sound weird. I'm not sure how loud they'll be. So click them and you can see the frequency. Hopefully you should be able to hear, because our brains are programmed to be able to hear this kind of stuff. As you go up the frequency, the pitch goes higher. Okay, so the higher the frequency, the higher the pitch. And I want you to watch a quick video. This one, it's from on the Star Wars. What's wrong with that clip? Okay, I just want you to think about what is wrong with this clip. If we're being physicists and we're looking at just purely from a physics point of view. And once you've done that, that is your lesson finished. So, email me your work and then you are done for the week, and I will see you on Wednesday.